thing here. We're recording? We are recording, okay. Right, write that down. EMF, or electromotive force, and internal resistance. Okie dokie, got the title? Yeah, continue? Yeah. Okay. Electromotive force, also called EMF. So let's break this word down. Electro, meaning electricity. Motive, moving, yeah, and force. So, electromotive force, or EMF, what could that be referring to? Say again? Yeah, but like precisely what does that mean? No, but nice try. Yes, I understand what you're saying, that because the motive. So the reason, okay, we kind of think about the battery producing the voltage, you know, so there's something in the battery that gives the coulombs a motion and a voltage and sets them along, moving in the circuit, okay? Basically the EMF is the voltage of an electrical supply such as a battery. That's all it really is. I mean, we've kind of seen this used, really just means the battery's voltage, that's all. Generally speaking, it's the electrical potential for a source in a circuit. So it doesn't have to be the battery, I suppose, but it's usually the battery anyways. A device that supplies electrical energy is called the seat of the electromotive force, or EMF. And EMFs convert chemical, so Zachary, we had a good discussion about this. EMFs convert chemical, mechanical and other forms of energy into electrical energy. So they don't store it, but they rather convert it or produce it. The product of such a device is known as the EMF. Now you don't have to write all this down. When I look at the exams and they ask what is the EMF, usually they just expect the students to write the first sentence here. So it's enough for you to write the first sentence, but I would like you to write the first two, please, first two sentences. Oh, don't worry, Gina, I'll wait for you to write it down. No panic. Oh, is it easier for you to look off your phone? Yeah, okay. You got that, Dorian? Yeah? Are you feeling better? Yeah, okay. Were you very sick or slightly sick? Okay. Okay. You have that, Zach? Diego? Yeah? Which word are you on, Gina? Circuit, great. Okay, so that's EMF. So what's the difference between EMF and potential difference? For me, an EMF of 1 volt means each coulomb of charge is given 1 joule of energy. Whereas a PD or voltage of 1 volt between 2 points means each coulomb could do 1 joule of work. Or rather did 1 joule of work. Yeah, basically EMF gives a charge, a voltage. Whereas a PD, you're saying that a voltage was consumed. EMFs give, voltages, PDs take. That's roughly how I think about it. So, for example, yeah, I could say that this battery here is a 1.5 volt voltage, but really it's better to say the EMF is 1.5 volts. And the remote has a potential difference of 1.5 volts. But to be perfectly honest, I don't really worry too much about that. If you see EMF, it means it's a supply, always. EMF means it supplies voltage. Okay? Yeah. Now, I'm going to draw this again. It's an important circuit. Let me actually draw it for you. So, let's say we have a battery, like an AA battery, or whatever type of battery it is, and we'll have it have 2 cells, for example, like that. Okay, and there's the positive, and there's the negative. Now, what we do, we imagine this battery has an internal resistance. Now, please note, this is a, how can I say this? An imagination. It's not like it really has an internal resistor, because that would be kind of stupid. Like, why would you put a resistor inside your battery? It would make it run less efficiently. Okay? It's just we imagine, we model the battery as if the battery is made to have 2 parts, a perfect part and an internal resistance. It's like this, but it's not really this.
It's more like the resistance of the material.
Yeah, exactly, yeah. And many other things, I'm sure, yeah. But we can model it as if it's behaving like this. Do you understand what I'm saying? It's like this, but it's not really this. So, this has a pure EMF. And this has a small internal resistance. Now, we would like to know, what is this internal resistance? Now, we can't take the resistor out because there is no resistor. So we need some clever way to calculate the internal resistance. So what we do, let's connect it up to an external resistance, variable, we'll say, we'll call it R. And let's have here our ammeter. And then we want to also measure the voltage here. Now, usually you put the voltmeter around the battery. However, can you appreciate that that is the same as putting it here? That's the same voltmeter. Because what I could do, is it the same if I move this over to here? Have I changed anything? No. What about if I move it down to here? Have I changed anything? No. So what about if I put the voltmeter here, and I move this one down to here, and I move this one down to here? Any difference? Same thing. So the voltmeter here will get the same reading as the voltmeter up here. It's just common to put the voltmeter around the battery. Okay. We have seen a circuit like this before, haven't we? It's a little bit like the circuit for the IV characteristics. It's a little bit like it, isn't it? It's not a million miles away from it. Okay? Let's make some formulas. Using Kirchhoff's loop, starting here with the E, I say E and what do I get here?
Minus
Minus I or, and then back here, minus here,
small r.
yeah, I small r. That's equal to 0. That's just using Kirchhoff's loop. I think I have that here. Yeah. Now, actually, I suppose really this I or here is the voltage here, but we said that the voltage here would be the same as the voltage here. So really, I could just do this. Because we know the V. We have it on the voltmeter, right? Okay, and what else do we know? We know the V and we know the I, because we can read it here. There's two things we don't know, the E and the OR. Okay, so what? Yeah, okay. So with a little bit of rearranging, I can just say V equals OR times I plus minus. No, sorry, I'm confusing myself.
Minus E.
Sorry. V equals minus or times I plus E. Okay? Which are the variables? Which are the things you could change? If you change this here, this will change, and this will change, right? So what are the variables here? V and I. Okay? If you make a plot of V here and I here, what type of graph will you get? What shape will it be? Look at the formula. Linear. Going up or going down? No.
Going down.
Why? Minus or. So you get a graph that looks like this. But what is the interpretation of the slope? Minus or. And what's the interpretation of the intercept here? The EMF, E. Okay, so this circuit, if you plot some of the voltages and some of the current and make a line, then you can use the line to work out something that you can't access, which is the internal resistance and the EMF. So this is how, you know, the battery has printed on it the EMF 1.5 volts. You can calculate that 1.5 volts using a circuit like this. But what's also nice is you can also calculate the internal resistance, which is nice. Yeah? Okay. You have that? Yeah? Now, wait, just before you write that down, what do I think I made the graph already, and we have an example. Yeah, so I just want you to know that, one sec, sorry. E or I. E or I. E or. Yeah, this formula here, that's actually useful by itself, but there's nothing too special about this formula. This is just, how do we get this formula? By Kirchhoff's loop law. So it's not a new formula, but it's a useful thing to know for some of these problems. Okay, so the two results you really need, I'd like you to write all this down, but these are the two important things. Some questions will need this formula, and then some questions will need you to make the graph. Okay, you can copy that now. Now, I kind of like, sometimes people put the V on the y-axis and sometimes people put the V on the x-axis.
You just give one number.
Yeah. So. If the question didn't specify, then you might as well make your life a bit easier and choose the V on the y-axis. But, yeah. Be good. You got this? What? You're calling a racist?
That's just dull numbers on this one.
Okay, you got that? Continue?
Yeah.
So, I want to do this one first. A battery with EMF E and internal resistance or powers a resistor of 2 ohms. So what you have is, you have your battery, that's a battery, and you have here a resistor of 2 ohms. And when you connect it to the 2 ohms, you get 500 milliamps. Okay, so far? Then, when you replace the 2 with a 3, you get 400 milliamps. So if you replace this with 3 ohms, then this becomes 400 milliamps. And my question then is, what is the E and what is the internal resistance here? So if we use the Kirchhoff loop here, what did we say the formula was? E minus I or minus I or equals 0. So let's sub in the 2 and the 500, right? E minus 0.5 times 2 minus 0.5 times or equals 0. So you get E minus 0.5 or equals 1. Do you feel like you know what's going to happen?
Yeah, and you sum the other one.
Yeah. If we sub the other one in, we get E minus 0.4
Minus 3.
or minus 0.4.
Minus 3.
Oh, sorry. So that's going to be 1.2, isn't it?
Yeah.
Minus 0.4 or equals 0. So E minus 0.4 or equals 1.2. Now, what do I do with these two?
0.5. You just put 0.5 times 3. Or 0.4,
Is it okay?
Yeah.
Minus them.
Yeah.
Minus 0.5 minus minus 0.4 is minus 0.1 or 1 minus 1.2 minus 0.2. So the or will equal, in this case, 2 ohms, which is actually pretty big. And if I sub that in there, if that's a 2, then the E will equal 3 volts. Okay? So you got that by using Kirchhoff's loop. K-loop, I call it. And that's the first time I've called it K-loop, so that's a thing now. I'm going to make that my thing. K-loop, K-loop, and wub-wub-wub-dub-dub. Right, write this down. This is a section A type of question.
3 volts.
3 volts I got. What?
And be 2.
Of course, because 1 plus 1 is 2. Stephen. I have trouble with the easy ones sometimes. 2 volts. There you go. That's a sign of pure maths genius when you can't do the simple ones, by the way. And when you can't do the simple ones and the hard ones, that's a sign of math stupidity. So, you know. typical value is, Zach? I doubt it would. Maybe this would be an upper limit for what it would be.
It's from 2 ohm resistor in the circuit. We have a 2
Yeah,
power resistance of 2.
but that's not as unusual as you think.
Yeah.
And actually, if I have time, I want to do an example that shows you something interesting with this. Oh, you are all coming to the maths hackathon on Friday after Jones class?
What is that?
Remember, we're uploading the questions into the database.
So it's a hackathon?
Yeah. What's it? Ah, come on, you know this word, don't you? This is a new word?
Whatever fun, but why
Yeah.
the hackathon?
Hackathon is a computer-themed one. Groups of people working on some common objective, computer objective.
Hacking anything.
We're hacking the NCUK exams. We're hacking them up and putting them into the database.
Okay, I
Could
guess
that be
it's,
considered a steal of intellectual property?
Shh! Quiet!
What time is it again?
Huh?
What time is it again?
It's Friday all day after lunch, so you can come by after Jones class.
Oh,
it's gonna be a tough one.
Well, look, as I said to John, you know, if you want access to the database, you're going to need to contribute to the database.
That's true.
You can't just take. You have to give.
do we get like a special thing?
I'll have to think about how I want to implement a login system. Perhaps I could give you like a textual code or something, verification code. I don't know yet. Come on, it'll be great. You can bring your headphones, you can listen to some music, and you can just start copying and pasting. Come on, what else are you guys going to do on Friday? Don't pretend you have lives. Don't fool me.
What's that?
Exactly, yeah.
Engineers too.
Yeah, exactly. You're fooling no one. Okay, have you got that copied? Yeah. So, the second type of question with EMF and internal resistance is the type where they make you draw a graph. So, roughly, you don't have to be super accurate. I want you to do this question for me. I think you'll find it easy peasy. What will you put on the y-axis? The PD, yeah. And on the x-axis, put the I. And once you have the graph, I want you to give me the internal resistance and the EMF. And then after that, there's another example I want to do here. Are you doing this, Diego? Come on.
What is a suitable scale?
Voltage goes from 1 to 2, so you could go from go 0.1s up to 2, and the current go from 0.1s from 0 to 1s.
20 points.
Oh, you can count to 20, can't you? I think you first learn how to do that when you're 6, right?
I usually stop at the
Yeah, okay.
See, I wanted to use the lines in my book, but now I can't.
Okay, well just split the lines in 2. Come on, be an engineer about it, figure it out.
1, 2, 5, 6, 7, 8, 9, 10.
It's done. What's that?
Oh, sorry. I'm going to graph something else in a moment.
Well, mate.
Nice scale, it's definitely gonna work.
Well, it's just like that. It's alright.
What?
How
What?
do you get the intercept there? Because you started at 1.
Start it.
Did you start your y-axis at 1? Did you not care about 0?
Oh, I'm moving.
Okay, fine. Nearly got that, guys.
Still labeling the axes. Okay. 1 is 1. Yeah. To the most.
Okay, dokie, folks. What you get for the internal resistance? The slope.
Minus 1.
Yeah,
What?
1 or a half?
You mean the slope?
Yeah. What's the slope?
1.8.
Huh?
What did I do?
Y1 minus y2. So 1
What's the slope, Gina? -1.
is 1.
So the internal resistance is 1.
Yeah.
1. And what's the EMF?
2.
2. Yeah,
3.
it's okay.
Yeah.
Oh, come on, don't confuse me. Is it okay?
It's 2, yeah.
Right, there's a question I want to do for you now. Who's messaging me? Okay. There's a question I want to do. I'll put the values in here. You copy them down. Potential difference in volts. And current in amps. 1.75, 1.625, 1.5, 1.375, 1.25, 1.125, 1, 0.875, 0.75, 0.625. Current, 0.5, 0.75. You should be writing this down. 1, 1.25, 2.5, 1.5, 1.75, 2, 2.25, 2.5, 2.75.
It's going to be a quarter.
Yeah. Right. The first thing I want to do, make the graph. Insert, chart. No legend. Wait, hang on. Do I need to highlight them first, don't I? Sorry. Cancel. Try that again. Insert, chart, scatter. Right, so we'll call this PD against current. The x-axis is current in amps and potential difference in volts. Okay. I want the vertical lines too. There we go. And let me put in the trend line. And I want the equation.
Y equals minus.
And let me shrink this down a bit.
Minus 2.
Come on. Come on. I like my laptop, but the screen's a bit too small. Kind of annoys me sometimes. Let's shrink you down. Resolution. This is 800 by 600 pixels, man. Get a load of that. Okay, there we go. And then move this guy. Ah! Let me move my little equation box. How do I? Come on. Come on. Up, up, up. Whoa. There we go. Right. There. Now. So, what is the internal resistance? 2. And the EMF? 4. Now, I have many parts to follow this up, so I need to delete this graph. Can you just quickly sketch it? I don't want it accurate. No, I just want you to go dun-dun and draw a line and add this equation to it. A quick sketch.
Quick move to scale stitch.
That must be Lynn. Well, what the heck happened to you? Just an hour late?
No, just need to recover.
Okay. You can have your secrets. Right, have you drawn that? Yeah? Guys? Drawn? Yep. Okay. Can I delete the graph? Yep. Okay, deleting. Now, I want to go back to my circuit. Right, here's my circuit. I want to calculate the OR here. If I know the V, and if I know the I, how can I get the OR? Yeah. OR is what?
V over
V over I. Okay, so what I'm going to do now is add another column here to calculate the big R in ohms. And that will equal this over this. So what must have been happening here is you had the resistor on full and then you start to decrease the resistance to change the values of V and I. Is that okay? So before I continue, can you copy these down? You just need three significant figure, or one, how many do I want? I want, we'll make it 2 decimal places. If it's, whoa. The heck? Yes. There we go, that's better. Okay, add that to your table. Okay. You got those values? Yeah? Yes?
Gotcha.
Yes? Yes?
Yes.
Okay. Harry? Okay. So, now, next what I want to do is I want to know what is, where's my pen? What is the power coming out of this resistor? Let's say the resistor is a heater or a light or a computer or whatever. Okay? So, how can I calculate power? IV. So, let's calculate power now. So, that's power in watts, and that will equal I times V. So I have this. Again, let's make it just the 2. Oh, come on. Okay, now add that to your table. You got that?
Glasses aren't strong enough anymore.
How's that now?
Thank you, sir.
You got that? Harry? Yep. Now look, let's go back to the circuit one more time. So, there are 2 things in this circuit with a power output. There's this resistor here, and then there's this resistor here. This resistor could be a useful power output. For example, maybe this battery is connected to the remote, or maybe this is the battery inside a laptop, and this resistor here is the laptop. So this resistor here is given a name. It's called the load. It's usually the thing you want to power. This guy here, do we want to give this power? Not really. Oh, by the way, what form of work is this outputting?
Heat and sound.
Heat. Oh, do batteries make sound? I guess they could.
Coil one,
Well, mostly what form? Heat.
heat.
Do you notice when your battery gets hot? This is because the internal resistor is producing heat. Okay? So this is useful output and this is not useful output. What I want to calculate next is the power output of this guy. So its power is going to also be,
VI.
yeah, well the thing is actually, no, actually I don't want to calculate that just yet. What I want to do next, I'm going to make a graph, but just make the graph temporarily. But I'll delete the graph in a second. I want you to have a look at this chart. So what I'm doing is a graph of,
Resistance.
yeah, the power output of ore against,
Isn't it resistance against power?
against ore. Yeah. The x-axis is ore in ohms and that is power in watts. Okay. And again, let me just shrink this a little bit. Okay, what type of shape is this? It's not quite a straight line, is it? Is it? Is it a straight line? Not really. What shape would you describe this as? Let me put in a curve to help you out. Oh, come on. Oh, goodness. Hang on, I just. Okay. Oh. Right.
You have to get a pixel perfect.
That's screwed, I'm not drawing in the curve now. Right, okay. It's kind of a quadratic shape, isn't it?
Not really, but
Kind of. I mean, it goes up and then it comes down. Or if you prefer, this graph clearly has a maximum point,
Yeah.
doesn't it? Now, think about what that means. As you change the value of the resistor, you get different power. If you use a very big resistor, do you get a lot of power output?
No.
No. If you use a very small resistor, do you get a lot of power output? Well, actually, you can't quite see, but this continues down. Okay? Roughly speaking, what value of a resistor should you use to get the most power output? About 0.5, roughly speaking. Yeah? Now, what was the internal resistance earlier?
2.
What was it? Have a look for this one.
2 ohms.
Was it 2?
Yeah.
Are you sure?
Yeah.
Then, you sure it wasn't 0.5?
Y equals minus 2x plus 4.
Oh, flip. What the heck went wrong here? Wait. I didn't make the graph backwards, did I?
I think you did.
I did. Rats. That graph you drew earlier, I drew that backwards. I put V on the x-axis and I on the y-axis. I'm sorry. Can you change the labels? Just change V to I and I to V. I'm sorry. I screwed that up. I made a dog's dinner of that.
Wait, so in the table as well?
No. Just the graph.
Just the graph.
Yeah, the V and the I are the wrong way around. So just, the numbers are right. Just change V to I and I to V on your label. Sorry. Computers, you just can't count on them, huh? Right, have you changed the V to I and I to V? Yeah. Okay, now what's the internal resistance from the graph? Zach, you actually said earlier what it would be if you have the axes swapped around. The half, isn't it? Yeah?
Yeah, it should be a half.
Guys, look. If your graph is like this with V here and I here, and it's going down like this, then the slope is equal to minus 1 over r if these are swapped. Now, I'm sorry I did them backwards, but in fact, you can draw it either way. So I guess it's not totally bad that you've seen it the other way too. So what is the or here for this one? 0.5. Yeah? Now, look at this graph. What value of or gives you the most power? 0.5.
Maximum power.
Maximum power when the big or is the same as small or. That's the point here. If you have a battery and it has an internal resistance small or here, and you connect that to some external load with some big or here, and you want the most power, then what that means is you have to use an or that's equal to small or.
Why is that?
Well, you can see it on the graph. You get the most power when the or is the same as small or. It's just the way the graph works. Yeah. Seems surprising, doesn't it? So to me, that means the internal resistance in this battery should be the same as the resistance of the laptop itself. To get the most power output.
Kind of feels like that when they have those, when how much force you have to put in to get the biggest distance.
That's very good actually, because my next question here was, what does this remind you of? So you've said that you thought of one thing that's reminded you of where you had to match the frequencies. Yeah, it's very good. So the last calculation for this one is I want to finally finish by calculating what the efficiency is. Okay? So the efficiency is the power out over the power in times 100. Now the power out is this guy here. Right? So that's oh actually we know that. We can see it on the table. Where is it? At 0.5 roughly it's going to be, well hang on, sorry, can I delete this? Well, I need to delete it. 2 watts is the most I get when you have 0.5. Can you see? That's the most power, 2. Okay, so that here is 2 times 100. And power in, where's the power coming from? It's coming from the battery. What's the power the battery's providing? That will be IE. Because the battery provides E, doesn't it? And what do we say the I was at this value? 2. And oh, my EMF value is wrong from earlier. Yeah, but it's not really 4. We'll have to work it out. This is I, no, this is V, and this was I, and it crossed here at 4, didn't it?
Yeah.
And our formula should be V equals minus R times I plus E. Yeah?
Yeah,
So if I rearrange this, I get I,
4 over
Oh, don't confuse me. Or I equals minus
2A.
V plus E, right? So that means or equals minus 1 over or V plus E over or. Okay, so E over or equals 4. So E would equal 2. Thank you, Zachary. 2. So if I go back to my calculation, where's my calculation gone? Oh, there it is, sorry. 2 times the current. What did we say the current was? 2. 2 times 2? 4. So how efficient is this? Now that's not surprising because you have two things doing work here and they're both identical because they both have half an ohm resistance. So efficiency being 50% is not a surprise because what you've done is you split the work equally among the two, the inefficient and the efficient. Yeah.
It seems surprising because
Yeah, well that means that the most efficient battery you can make really is 50% efficient. And you achieve that 50% efficiency when you match the load with the internal resistance. And this is called load matching. Seems surprising, doesn't it? So I hope this might make a little bit of sense to you. Why do laptop batteries get so hot? Well, because the resistance in the laptop battery is the same as the resistance in the laptop. If the laptop requires a lot of battery power, then that means the internal resistor is getting the same amount of power. And so the amount of heat you feel from the battery should equal the amount of energy you're getting out from the laptop, if it's being matched. Do you get what I'm saying? So I would imagine, for example, your phone. The phone battery will get hot, and phone batteries should be hotter for phones that need more power. And it's nothing really to do with the battery necessarily, you know, because we've just seen the most efficient way to do this is have the load match the battery's internal resistance. Now you don't have to have them matched, okay? You could have them not matched, but this means you're less efficient.
But you could have, say, a larger capacity.
But you could have just a larger battery, and so you could produce less heat this way. You know, it depends what you're trying to achieve.
Maybe the point shifts, like at the point where the battery becomes large enough, it would last longer than if it were more efficient with a lower capacity at the same size.
Yeah, I suppose if the battery was big enough, you might not care about the efficiency. So, yeah. Anyways, I think this is a very popular question in the exam because there's probably a load of questions in the database for this one, is there? 20?
There were like, yeah. 17, 19, 20, 21, 22.
22.
So what I'd like to do, I want to get started on the next lesson, but I want you to try one or two of these for 5 minutes only. And then we can at least get a start on the last lessons for the semester.